So the next part of this chapter, we talk about the Bohr model of the atom. So this comes after Rutherford and Chadwick and J.J. Thomson, all those people. So Bohr basically said that the electrons are indeed outside the nucleus orbiting, but they orbit in specific orbitals around the nucleus. So Niels Bohr came up with this idea. His model shows the nucleus at the center, right in this area, and it says the number of protons P and the number of neutrons N within the atom. That's how you can identify the atom without naming it. So it says magnesium, but if we didn't have that, we would still know this is magnesium. And then it shows the electrons in their surrounding orbitals. So level 1, the first electron orbital can hold 2 electrons, up to 2. The second can hold up to 8. The third can hold up to 18. And then the fourth can hold up to 32. So you have to fill each level before moving on. So in magnesium, you'll notice that the first and second levels are full, but the third is not. That's because we only need 12 electrons, and we have 2, 4, 6, 8, 10 in the first 2 orbitals, and then 11, 12. So you're not going to draw circles, orbitals that you don't need, and you're only putting in the number that you need total using this information. So let's practice. So draw the Bohr model for carbon. So you're going to draw a circle and kind of shade it in a little bit. That's going to be your nucleus. And carbon is C. Looking at the periodic table, carbon's atomic number is 6. Remember, this is going to tell us the number of protons, and it's going to tell us the number of electrons. Then, looking at carbon's atomic mass, it's about 12.001. So I'm going to round to 12. And remember, to find the number of neutrons, you take the mass minus the atomic number, and you want this one to be a whole number. So 12 minus 6, atomic mass of 12, minus 6 gives us 6. So there's also 6 neutrons. So in the center here, I'm going to write 6p for protons and 6n for neutrons. And then now I need to actually fill the orbitals. So I have 6 total electrons I'm looking for. The first sublevel can hold 2. So 6 minus 2 is 4. I need 4 more. The second sublevel can hold up to 8, but I only need 4. And you can put these kind of wherever you want, just space them out. And then I check 1, 2, 3, 4, 5, 6, and I don't need the outer ring. I don't think I have a white, but basically you're just going to ignore this outer ring. You don't need it. Okay, so you're going to have the nucleus kind of shaded. You don't have to write nucleus, but 6p, 6n. And they're going to have the first level with 2 electrons, and that's all the first level can hold. You need a second circle for the second level, and that can hold 1, 2, 3, 4, up to 8. And that gives us a total of 6 electrons. So that's the Bohr model for carbon. Let's try another. Okay, Bohr model for nickel. Nickel is Ni. It's important that you have the right symbol, find the right one on the periodic table. Its atomic number is 28. So this means it has 28 protons and 28 electrons. And then to find the number of neutrons, I take the mass of nickel, which is 58.69. But I want a whole number, so I'm going to round that to 59. So a mass of 59 minus atomic number of 28. Do the subtraction, you want a whole number. And I get that there are 31 neutrons. And you have to round this up to 59. You have to use your rounding rules. So in the center, shade your circle. I'm going to put 28 protons, 31 neutrons, and then I need 28 electrons surrounding. So level 1 can hold 2, 1, 2. Level 2 can hold 8, 1, 2, 3, 4, 5, 6, 7, 8. That gives me a total of 10. I need 18 more. Level 3 can hold up to how many? It can hold up to 18, and that's how many we need. So we only need 3 levels in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And adding all this up gives us 28. So this is a Bohr model for nickel. Levels 1, 2, and 3 are filled in completely. Okay, moving on. Pauli exclusion principle. This man basically said that no 2 electrons can have the same 4 quantum numbers. No 2 electrons can be in the exact same level, in the exact same sublevel, in the exact same orbital, rotating the exact same direction. Okay? If they are in the same level, sublevel, and orbital, they have to at least be spinning the opposite direction. So that's a Pauli exclusion principle. And then the Heisenberg uncertainty principle basically says, although we do know that these quantum numbers are pretty accurate, because the electrons are so small and they're so rapidly moving at all times, it is not possible to know the position and the speed of an electron with certainty. We can guesstimate their location, their sublevel, their energy level, their orbital, their rotation, but it's not possible to know 100% accuracy on this because they're so small and they're just constantly moving. So the big takeaway from this section is that Bohr model of the electron or of the atom, you have your nucleus in the middle with the number of protons and neutrons as a rounded number, and then you have the orbitals surrounding it filled by level 1 has 2 electrons, level 2 can have up to 8, level 3 can have up to 18, level 4 can have up to 32, and then after that 5, 6, 7, 8 can also hold 32.